Play the music. Guys, welcome back to the Off-Grid Garage in sunny, hot Australia. Look at this, huh? Isn't that nice? Solar weather, finally. Yeah, it is 11:30 and we already have 3.4 kilowatt from our 4 kilowatt system. Well, not quite sure because I still have the fence solar system up and running as well. So technically we would have a 4.6 kilowatt system, so 3.1 is not that good. I think today is the day when we will fully charge both batteries and experience both BMSs, the QUCC BMS, the QUCC BMS here in the old battery, and the JK-BMS with a new battery here, and see how the whole system performs when we fully charge them to 3.45 volts. I also want to go a little bit further, potentially up to 3.55, 3.6 even, to see how the balancers work in the JK and the QUCC, if there is any interference between these two, and just experience and of course share here how the whole system performs at a very high state of charge, high voltage, and potentially a high voltage disconnect again. Let's see. And of course I will start the screen recording here in just a minute. So we're currently charging the QUCC battery, the old battery, with 25 amps, and we've got a deviation of 19 millivolt. So this shows me we are still in the flat part of the charging curve. Even we have exceeded here 3.4 volts. There's a second cell and the other ones are just below 3.4 volts. So, but again, this is charging voltage. This is not actual cell voltage. Let's have a quick look at the JK-BMS here. 33 amps, a bit more energy it takes. And deviation is 11 millivolt there. And here again, we are just around 3.4 volts with our battery cells. So this all looks pretty good so far. The Victron Smart Shunt claims we are almost at 90% state of charge here. I'm sure this is not right. I think we are a little bit further or below. I really cannot tell you. This is like, I cannot remember when we have fully charged the old battery. I really cannot remember. I really rarely fully charge my batteries. I just cannot remember. Okay guys, I would say I prepare everything for the screen recording here, and then I'll be back once we are hitting 3.43, 3.45 volts or something. So once we are leaving the flat part of the charging curve and going into the knee, into the, not the knee, into the knee, into the steeper area of the charging curve. And this morning I have turned off all the load of our system here. Pool pump is turned off, car charging is off, irrigation pump is off. There are just a few standby devices here. The light is running and the fan, because it is sunny, hot Australia. You need to have a fan, right? Yeah, and again, 3.45 volt per cell is when our solar charge controllers stop going higher with their charging voltage. This is when they reach the absorption voltage and keep the voltage constant. And from there on, the batteries will still take power, but you can see then the current curve usually tapers off fairly quickly. This all depends how good these cells are already saturated and absorbed. If you charge the batteries very slow until this point, the absorption time can be very, very short, because the batteries are already saturated. And the opposite, if you charge your batteries very fast during the day, the absorption time can be a lot longer. And I've made this video about it here. I compared all the different charging speeds of one battery, and we came exactly to this conclusion, that charging speed matters and influences your absorption time a lot. I'll link this video down below in the video description. That was a fantastic test and a very interesting result. Yeah, and here's another indication that we are not there yet, because we just have a cloud coming in front of the sun, and you can see the charging current goes down, and so does the cell voltage. The battery is not saturated yet, it's not absorbed yet, it cannot hold the voltage. As soon as the sun goes away with a cloud and the charge voltage actually drops, the cell voltage drops as well. If the cells would be absorbed already, they would hold the voltage, but they are clearly not. So it may take another half an hour, hour or so until we are there. So I'll go back in the garden, do some work, and I'll be back soon. Oh, now the sun is back. 29 amps, 40 amps. No. Ah, wait, there's another cloud coming. So here we have the settings of both BMSs, the QUCC on the left and the JK-BMS on the right. I just want to prepare everything for our high state of charge test, our high voltage test here for these two BMSs. And I just saw I have set the QUCC on the left to a 3.66 volts over voltage protection. I'm not sure if we go that high, but I just set the QUCC to the same value. There we go. Okay, and then we have an over voltage release of 3.6, and I'll do the same here on the JK-BMS. The start balance voltage in the JK-BMS is 3.45, and I'm sure it's the same here. 3.455 I've set here. Okay, let's change this one to 1 millivolt deviation on the QUCC. And here we have, what do we have here? And can we not set a, I can't remember. I cannot see here. Up, it's all the way up in the basic settings, balance trigger voltage, 5 millivolt. 5 millivolt is totally fine. I can potentially set this one as well here in the QUCC BMS. Confirm. So 3.45, we're starting balancing, and then down to 5 millivolt precision. This is basically all we need for the moment, at least here in the JK-BMS, because this is all cell based. So we don't have an overall pack voltage here we can actually set as a trigger point for over voltage protection, but we have this here in the QUCC. See, there's a pack over voltage protection. I'm not 100% sure why they have included this, because if you reach this voltage, clearly one of your cells has an over voltage situation already, and the BMS would trigger anyway. So I don't find this very useful to set a pack over voltage or pack under voltage protection at all in the BMS. This is all we need to check. 54.5 volts, 15 millivolt deviation, JK, and 18 millivolt in the QUCC. Again, this shows we are still in the flat area of the curve. Otherwise, we would see some deviation, some voltage difference already in the cells. Okay, we'll leave this running here for a moment, and then I'll be back once it gets interesting. Well, we have just charged with over 4 kilowatts here, and I could see a really large imbalance in these batteries here. 3 amps, 2 amps, 13 amps. There was like 2/3 of the energy went into the JK battery and only 1/3 went into the QUCC battery. But this again could be because we've got the terminal issue still with cell number 6 and some other cells. So we have an overall higher resistance in this battery, and therefore it takes less energy. And this one is now perfectly connected here with the aluminum bus bars and the no oxide paste, and there was no further issue when charging the vehicle or something. This was all perfectly connected, no heating up of bus bars anymore, nothing. They're all staying metal cool. Perfect. Yeah, just another cloud. 7 amps, 0 amps. Nothing goes in the QUCC BMS anymore. Or 2 amps now, it picks up again. So it looks like there is a bit of an imbalance between the new battery and the old battery. Each battery gets as much current as it needs to stay on the same voltage. It's a self-balancing system. Almost no current, and we can see some of the cells actually stay above 3.4 volts now. So they are already absorbed. And I think this one has a fairly large imbalance, which we will see when we hit the 3.45 volts. Well, this one should be fairly okay-ish, but I don't know. It's the first time I'm fully charging this battery now in this configuration. And here the Victron Smart Shunt shows us we are 19 ampere hours short of 100%. But again, this is not calibrated, and I had to reset the whole situation a few times when we disconnected the batteries and did other tests. So this is just a rough guess what I put in the system, and the shunt took it and calculates from there. We can see the first cell gets balanced here in the QUCC BMS because there is a deviation of 60 millivolt already, and there's a second cell actually getting balanced. Well, there's nothing in here. Balance 0, 13 millivolt. And I must say I'm really impressed with the new battery here. We are charging with 46 amps, so 2.5 kilowatts, and we still have a deviation of 14 millivolt only across all these 16 cells. So the connections are really good now in here, in big contrast to the QUCC BMS or battery here, the old battery, which has a lot of issues with connections. See, cell number 5 is the lowest. We've got already 82 millivolt deviation. Some of the cells are actually balancing already. Here, number 15, number 1, and there was one here as well, I think number 10. Yeah, number 10 and number 14 are already balancing. We are still not there yet. Look at cell number 10, the blue one. 3.449. At 3.45 we will see balancing happening. There you go. Cell number 10, 3.45, and the balancer turns on. We are balancing here as well. 20 millivolt. Oh, there, 20 millivolt deviation only. So this is now discharging cell number 10 with 2 amps, and it puts this energy back into cell number 9, which is our lowest one. So it equalizes all the cells now automatically. Well, this one here has only a passive balancer, and it balances all the cells with a green B at the end. Yeah, quite a few. By discharging them with 0.2 amps, which is kind of ineffective because we are still charging with 12.6. So these cells, which are getting balanced at the moment, are getting only 12.4 amps then instead. Kind of ineffective. Wasn't cell number 10 our low voltage disconnect cell as well in the previous test we did? Are we seeing something here, cell number 10? Is this our new cell number 6, which is always high and always low? Let's earmark that. So we now leave the system running here for a while at 56 volts, which is 3.5 per cell. And we want to see what the actual differences are. So here on the QUCC we've got 160 millivolt deviation, and on the JK-BMS battery here 138. So this has increased as well. But we can also see that cell number 10 is not our highest cell anymore here on the JK battery. It is now cell number 16. So obviously the balancer has already brought down cell number 10 quite a lot, so that another cell could catch up. If we can see the same result in the QUCC BMS, I have my doubts. Because passive balancing with 200 milliamps will take a long time with these high capacity battery cells we have. Okay, let's leave it running for say half an hour, and then we have a look what the result is. And then we potentially increase the voltage again just a bit to see what's going on. And here we can see the balancing of both BMSs in full action. On the left there's the QUCC BMS with its passive balancing of 200 milliamps, and it's very desperate to discharge the higher voltage cells. You can see the green B is behind all these cells which are higher. And here in the JK BMS we can see cell number 16 is high, over 3.6 volts already. So this is the highest cell as far as I can see. Yeah, that is the highest cell by far. So obviously quite a bit of imbalance here in this battery as well, 160, but the active balancer is currently discharging cell number 16. You can see it flashing, and now cell number 5 flashes, and the balance current turned positive. So it's now charging cell number 5 with an additional 2 amps. And it does a great job to keep cell number 16 under 3.65 volts, which then would mean the BMS would turn off charging altogether for this battery. See, now it's discharging again, cell number 16, and you can see the voltage dropping already while it is discharging and balancing this cell. It goes down fairly quickly. 2 amps balancing current, active balancer in the JK, versus the 200 milliamp on the left, passive balancing.
One hour later.
So, well, it is now a bit over an hour since we left the 2 batteries here sitting on absorption voltage of 56 volts, which is 3.5 per cell. And on the left, the QUCC battery started with 160 millivolt deviation, and it has now reached 265 millivolt deviation. So it got even worse. And this is because, well, see, cell number 7 and 9, they are really, really low. They are under 3.4 volts, far under 3.4 volts. But there's no current going into the battery anymore. So how can we recharge these cells? We can't. And the only thing the BMS can do is now discharging the high voltage cells with 200 milliamps, which then triggers a little bit of current into the battery again, but this is not enough. This will take hours now. It would potentially work overnight and could balance our battery until the next morning, but usually you don't leave your battery on absorption voltage for that long. The JK-BMS with its active 2 amp balancer, we started with 158 millivolts and we are now down to 12, I've seen 9 millivolt already, deviation only. So it almost has balanced the full battery within this hour. And there you can clearly see the difference between an active 2 amp balancer and a passive 200 milliamp balancer. The QUCC BMS cannot cope with these high capacity cells at all. And imagine if you have a Dali BMS with only 50, 60, 70 milliamp balance current. It gets even worse. Of course, there's the opinion, well, if your cells don't exceed the specifications of the manufacturer, either over exceed or under exceed, it is all good. You don't need to balance at all then. As long as your BMS's balancer manages to keep these cells under control, so they are not going over 3.65 or under 2.5 volts, it is all good. It doesn't really matter how much the deviation between the cells is. And of course, you could use the QUCC battery as it is at the moment here, just totally fine, even with the 270 millivolt deviation you have. Because of this imbalance of the cells, you cannot expect to have the full capacity of this battery. And on the right, the JK-BMS is almost finished balancing, 6 millivolt deviation. If we go under 5 or to 5 millivolt deviation, then the balancer turns off already. This was the threshold we set in the BMS. So this BMS with its active balancer is really impressive. Okay, let's try the 3.55 times 16 is 56.8. So again, we go into our west roof, which is the mothership of our solar charge controllers. 0.8. Right, so this is 3.55. And now we will see the QUCC BMS will shut down every second. 3.6. There it is. That's the warning. Another warning. There we go. There's our relay. Charging has turned off. And now the balancer is still working, which is good. This is the good part on the QUCC. I think it won't stop beeping until we go under 3.65 again. And now the passive balancer will actually discharge all these high voltage cells. But it doesn't help cell number 7 and 9 because there's no current coming in anymore. while the JK-BMS has no trouble keeping all the cells under control. 10 millivolt deviation at 3.55. And I hope the beeping stops at 3.65. So now we also have a voltage difference in the battery banks. The QUCC battery 56.2 and the new battery 56.9. But again, the active balancer does a fantastic job to keep all the cells in balance. 7 millivolt deviation we have. The pack is so nice balanced now. Great. Oh, it has stopped beeping because, I don't know. The cell is still over 3.65 volts, but thankfully it has stopped beeping. So there you go. We are running the whole show with one battery now again. The QUCC BMS has turned off one battery bank due to a cell overvoltage situation. And we are running the whole system from the JK, from the new battery with the JK BMS, which still gets balanced. And we are now at 5 millivolt deviation with this battery. And because we have set 3.6 volts as the recovery voltage, the QUCC BMS will wait until we reach this voltage with cell number 5 now, which is the highest. And then it will turn on the relay again and connect both battery banks together again. And then there could be some current from one battery going into the other one. Let's find out. And I would expect cell number 5 will peak again immediately and turn off the relay again. So the old battery with the QUCC BMS will bounce between 3.65 and 3.6 volts all the time due to cell number 5. And then it turns on and off the relay accordingly. So let's see if we can see the balancer turning off in the JK BMS. It's at 5 millivolt. If it goes further down to 4 millivolt, it should turn off the balancer. There it is. 4 millivolt deviation, 0 balancing, as we set it in the settings. See, the JK BMS does exactly what you set in the settings, while the QUCC is sometimes a bit hit and miss, and we don't really know exactly when the relay actually triggers turning off and on. And we can actually go to 3.6 volts, 57.6, just for a test. And this will affect only our JK BMS with the battery, with the new battery now, because the other one is still turned off. So increasing the voltage even further here in this battery now. Man, this takes forever for the QUCC BMS to discharge cell number 5. We are still at 3.619. I'll take the car lights and discharge the cell manually. Just a tiny bit. So if it goes under 3.6, it should turn on the relay. And then I want to see how much current actually flows into this battery, because the voltage difference is quite high now between the two banks. So let's see what this actually triggers then. I hope nothing explodes. We need to stay under 3.6 for a few seconds to make this work. Okay, I'm discharging a little bit further. Then we should hear the relay clicking again. 3.6. 20 seconds delay. Okay. Well, this is well and truly over 20 seconds now. Say another cell over 3.6. Ah, there's cell number 12 as well. Ah, that's why it doesn't turn on. Okay. Let me discharge this one as well. And then it takes 20 seconds. Okay, relay is on. How much amps? 51 amps. Wow, 50 amps it gets. And then cell number 12, 3.7. It totally shoots over now, because there's so much current going in. Cell number 12, 3.7. Cell number 5, 3.7 as well. That is shit. Okay, it has turned off again. But look at cell number 5 and cell number 12. Totally overcharged now, over 3.65 volts, because the battery is so imbalanced. That is insane. It will beep forever now. Well, the JK BMS cruises along with 6 millivolt deviation here at 3.5, now 3.6 volts. Okay, just closing the lids, not that loud then anymore. Okay guys, so far this video from today, the other test, the high voltage, high state of charge test with both the old battery and the new battery in parallel. So that was very interesting to see as well. The old battery obviously a bit out of shape, a bit out of balance. It will take some time to get this back in balance, but I'm not bothered with this at all. We want to take it offline anyway soon, and then do a full maintenance and capacity test on all the cells. Repair all these stripped cells, of course. That'll be an interesting video coming up soon. And usually I charge only to 3.45 volts per cell, and there was no issue with the old battery or with the new battery. They were all perfectly fine within the specs. And I will keep it like this. 3.45 volts is my maximum voltage. This is 99.99% already of the capacity after absorption. Why would you go higher and risk that? 55.2 again, which is 3.45 volts. This will now discharge our batteries, well, at least our JK battery, because the MOSFETs are still on. But here the relay is turned off because of a high voltage disconnect still, and it won't even discharge now. So we have to wait for the balancer to catch up and discharge the cells, so the relay turns on again eventually, and then it joins the other battery again at 55.2 volts. It also shows that active balancing is far superior to passive balancing in these BMSs. Well, within 1 hour, the JK-BMS balanced the whole battery just fine, while the QUCC BMS actually increased the deviation across all the cells. And until the next video, guys, you stay charged and safe. And also thank you again for watching and all your generous support here on the channel. Thanks again, guys. See you then. Bye-bye.